Congratulations, you've made it to the end of these live lessons. I'd like to take a moment to rehash a topic from the very beginning. We started off by talking about three categories of artificial intelligence. We talked about artificial narrow intelligence, which are these very specifically defined problems, like classifying MNIST digits, classifying movie reviews by their sentiment, generating fake handwritten images with our generative adversarial network, playing the cart pull game. These are examples of very narrow intelligences. So even if we can create the world's best cart pull player, that cart pull playing agent won't be very good at generating MNIST digits or classifying MNIST digits, and certainly classifying natural language documents. So what we're trying to progress towards is an algorithm that possesses artificial general intelligence, and then that can be applied in the same kind of way that you and I use our intelligence across a broad range of problems. And then there's this theoretical idea of artificial superintelligence that may be even better than you and me. If you'd like to learn more about artificial general intelligence and artificial superintelligence at a high level, check out Tim Urban's wonderful, lengthy, comprehensive post on the topic on his Wait But Why blog. It's called The AI Revolution, The Road to Superintelligence. We're going to talk about a few of the factors that are driving AI in general, whether we're talking about narrow or artificial general intelligence. The first one is data. So data sets have become larger than ever, they're becoming cheaper than ever, and the critical piece is that they're becoming better organized and accessible. The second factor driving AI is computing power. So this is CPUs, which are following Moore's law, and the GPUs that have become popular in deep learning research since 2012, parallel processing across many CPUs and GPUs, and of course, across all of these approaches, whether we're talking about CPUs, GPUs, or parallel processing, all of these are becoming exponentially less expensive. So compute power is definitely going in the right direction. The third factor driving AI is algorithms. So these are all of the topics that we've listed on the whiteboard here as a starting point. And this is rapidly improving. Deep learning research is evolving quickly as more and more researchers and industrial practitioners pick up deep learning approaches to solving problems. You know, getting onto this software 2.0 train with the rest of us. The fourth factor driving AI is infrastructure. So this is open source operating systems, open source libraries, and the inexpensiveness of cloud computing. So these things are moving along as well. So how come we don't have artificial general intelligence today? Well, deep learning is a great candidate for artificial general intelligence down the line, but there are major barriers today that make it completely impractical. The first one is that today we need to train on many, many samples of data. So deep learning algorithms don't learn like you and I do, or even like a puppy does, where just a couple of examples of training allow learning to happen. Instead, we need often thousands or millions of samples to have deep learning algorithms learn complex tasks. The second problem is that deep learning algorithms are a black box. So they're black box nature. There's some people kind of working on that problem, trying to visualize what layers are doing. And this is one of the strengths of deep learning in a way, because it allows an incredible amount of flexibility. We couldn't possibly probe into what the millions or billions of parameters in a deep neural network are doing and understand that. So in some ways that's a strength. But the drawback is that it makes it harder for us to learn from what's going on there and to improve the overall ideas underlying a given deep learning architecture. The third barrier is that deep learning algorithms don't do a good job today of leveraging knowledge of the real world. So the ability to incorporate factual information, particularly changing factual information about the world, this is not handled well by today's deep learning algorithms. The fourth problem is that deep learning algorithms cannot today distinguish correlation from causation. So It's very good at approximating complex functions between some inputs x and some outcome y, but it doesn't have an ability to distinguish when there's just two things happening at the same time or that one thing is causing the second thing. And so this is a key limitation. It's a very important ability that you and I have that deep learning algorithms today don't. The fifth point that sometimes leads to news headlines is that deep learning algorithms have sometimes unintuitive, embarrassing, or deliberately adversarial attack failures where the algorithm is expected to behave in a certain way, but it behaves completely differently. And because of the black box problem, we can't even explain why these problems are happening. Despite these barriers, deep learning is by far the strongest candidate today for approaching the theoretical achievement of artificial general intelligence some decades from now. So it's great that you're interested in this. I hope you've enjoyed learning about all of the underlying theoretical foundations, bringing them all the way up to state-of-the-art deep reinforcement learning approaches. These are really exciting times, and these barriers that are in front of us, maybe you've been inspired to tackle one or a handful of these yourself.